Hello. In this video, we are going to discuss the natural logarithm. Um, as you compare my videos and notes to the textbook, you'll notice that I'm skipping a section. The textbook went up an edition, and suddenly we have two sections on logarithms instead of one. But the natural logarithm is the only logarithm we're going to use in this class. So, I mean, if you've never seen logarithms before, it might certainly be helpful to look at the previous section, but it's not calculus, and it's not really what I'm here to teach you. So I'm just going to briefly introduce the logarithm that we actually are going to be using. So the natural logarithm is a function written f of x equals ln x. I'll show you the graph in a moment, but for now, I'll just state some facts about the natural logarithm. We'll, I guess, start with the most important one. It is the inverse of e to the x. I mean, this is the definition, really. This is how the natural logarithm can be defined. And what this means, I mean, it really means two things. It means that the natural logarithm of e to the x equals x. And for our purposes, this is the important one. It means that e to the ln x equals x. The natural logarithm is only defined when x is greater than 0. The natural logarithm of a negative number, the natural logarithm of 0, these things are not defined. It's increasing and it's concave down. And let's take a look now. Here is the graph. So it has a vertical asymptote at 0. It's probably not really obvious at this magnification, but if I zoom in, you see that as x approaches 0, this curve is plunging down to negative infinity. Another way of saying that is that initially, this function is increasing really, really fast. I mean, if you think of the tangent line at this point, it's going to be almost vertical. It's going to be increasing extremely quickly. But because of its concavity, after it increases extremely quickly for a bit, it starts to increase at a much slower rate. In practice, we're usually looking at the logarithm out here where x is probably greater than 1. And the logarithm, because of its concavity, is extremely slow growing. Like if we let x go all the way out to 10,000, the logarithm is still sitting around 10 or so. So it's an increasing but extremely slow growing function. And for our purposes, that's almost enough. The textbook section that I'm skipping does a lot of stuff on using logarithms to solve exponential equations. And again, that's college algebra. I mean, I'm not saying it's not important, but it's not what we need to be talking about. Though one other thing I do want to say about this function, I mentioned that e to the ln of x equals x, and I said that this is important. Why is this important? Suppose we have an exponential function whose base is not e. Suppose we have 2 to the power of x. Well, looking forward a bit to later sections, we're only going to learn to do calculus with e to the x. So what's this mean about 2 to the x? Does it mean that we can just never take derivatives or never do anything? If we see it in the wild, we just have to throw up our hands and give up calculus as a tool? Well, it means nothing of the sort. Because according to what I have written up here, that e to the ln of x equals x, this is true for every value of x. So it's true for 2. E to the ln of 2 equals 2. So we can rewrite 2 to the x as e to the ln of 2 raised to the power of x. And then a power raised to a power, you multiply the exponents. So this is e to the ln 2 times x. So I don't know that you need to commit this to memory, but it's really significant that if you have a base other than e, if you have b to the power of x, you can always rewrite that as e to the natural log of the base times x. So this is how we're able to get away with only doing calculus with base e exponential functions. Because if we have another base, we can use logarithms to rewrite it as a base e exponential function.